Alrighty, welcome back. So, today, what I'm planning to do is the following. Where's my, it's here. So, what I'm doing right now is I'm trying, as a complete noob, as a complete beginner, I'm trying to grasp my head around concepts of deep learning. And what I did up until now is I passed the basic stuff. So there's like the basics of the NumPy library. Then we did some basic functions, some derivative code, which we learned from math already. Then there's something that's known as chain length or chain rules. And we also graphed this. We graphed the chain rule of two methods that are in a chain, and also we graphed their derivatives. So now, let me just create a new markdown here at the end. I'm gonna call this chaining three derivatives. Okay, chaining three derivatives. I have you add a new code. Okay. So just to make things clearer now, hope you like my wallpaper here. So just to make things clearer, what I've been doing here is I've been learning about longer chains. So this is the formula on how longer chains are differentiated. This is a visual representation of it, and that's it. So now I'm trying to code this out. So I have chain derivative 3. I have a chain an input range, which is an NumPy array, produces the same thing. So let me just do some assertions. I'm gonna just copy them from the book I'm following. Nice. So now what I'm trying to do is to translate this formula that's written in purple text, in purple handwriting, into the code. All right, let me just take a look at it. Okay, f1 of x is f1, and we take the input range. What else? f2 of x, so it's gonna be f2 f1 of x. What else do we have? We have the derivatives. And how is the derivative? How is the derivative produced? I have the derivative method. What's it? What's the derivative method doing? Okay, it adds the delta and calculates the slope of a function here, it seems. So I want to derive what? So it's f3, f2 of x, which is basically this, what I just show you. So it's this part, it's the derivative of f3. So basically I handled the derivative part by using the derivative method that I already have, and I'm producing here, if I'm not mistaken, the arguments. Yeah, so I have the function, I have the input, all right, and I have the delta. The delta, it's an approximation, so we don't need it here. And what basically happens here is that we call the function on the input data, and we add the delta, and we calculate the derivative. Same thing here. F1 of x, and also here, but this is done on dx, so it's going to be a derivative of what? Okay, so let's think about, let's do this without looking at the book. So it's just going to be the function f1 based on the input range. And then if I return a multiplication of all of these quantities, this should be enough. Execute above cells, execute this cell as well. Is it working? Continue. Have I put? No, I didn't. What? I thought I have a breakpoint somewhere. Alrighty. Hey Sadat, what's up? Sorry, I don't answer you. I'm trying to learn these things. Oops, I'm sorry for the sound you just witnessed. Hey man. Okay. Okay. All right, so now this code is doing something interesting. So we are computing the derivatives for our nested, let me just remove this, for our nested functions or composite functions. And we have the chain rule, which works here in the formula that I just shown you. So what does it mean to go forwards or backwards? So we are evaluating a function, and we are evaluating a chain of functions for a given input that we have. We compute the result in order from the input to the output, and this is called the forward pass because it goes step by step from the input to the output. So we have the input range here. We have the input range here, and then we compute the value of the first function applied to the input. So it's here. This is a forward pass, and then we use the output of f1 as the input to the second function here, and now we have the output of f2, and we can do the same thing for f3 as well, if it exists. So with the forward pass, we build up the intermediate quantities that we'll use later to compute the derivative. So I'll just write this down because it might be useful. Okay, so I'll just write it here. Forward pass versus backward pass. All right, so something to remember. Now, the backward pass involves computing the derivatives step by step in reverse order. So we start from the final function and propagate the derivations back to the input. And now this is where the chain rule comes into play. So we have here the backward pass, where we start with the derivative of the last function with respect to its input here, which will compute the rate of change of the f3 function with respect to these inputs here. And we multiply this by the derivative of the second function, and then we multiply this by the derivative of the first function with respect to the input, which is this right here. And then we combine these derivatives, and that's it. And why do we have two passes here? So the forward pass is computing the intermediate values that require that the functions themselves require, and backward pass is propagating the derivatives back from the last function to the first function, because that's how the chain rule works when calculating derivatives. All right. So let's hope that this works. I'm gonna save this. I'm gonna add a new code snippet. I'm gonna copy this. So we have a plot range ranging from -3 to 3 with a 0.01 difference. And then we are chaining all of these methods that we have already written above. Plot chain derivative. What? Plot range. Am I missing something here? All right, will it work now? Why is it, is this a debugging? Run all maybe. Yeah, run all is working. For some reason this is debugging it. It's run by line. Okay, my mistake. What does it say here? I have an error. What kind of an error? In line 19 I have the plot range that I created. Module numpy has no attribute range. How? How? NP range. How does it? What? -3, 3. Where else have I used this? NP range. So I need to. Okay. I need to import the range. Let me just. See how it's done. All right, seems like I'll need to rewrite this because this doesn't work properly. Okay, do I have all 3 of these methods? I think I should have them. Leaky relu, sigmoid, chain rule. Yeah, I think I have them. Maybe just in case, let me add them here one more time. Alright, so module numpy has no attribute named range. Plot chain. Is this taking a, yeah, it's taking a general chain here. So I'm just gonna copy this and I'm gonna explain you what this does in a moment. I just want to make sure this works. All right, run all, save. There's an error. Plot chain got an unexpected keyword argument length. Line 7, plot chain, it's here. All right, let's also import the plot chain and plot chain derivative here again. Nice. And I'm just gonna add the chain of length 3 here. I'm just following the book. I'm trying to see. Okay, this works. This works. This looks unruly. So what has been right? So let's start from this guy here. So we have in this code snippet we have two functions. We have the chain derivative tree and we have chain length tree, which are used to compute the evaluation and derivative of a chain of three functions. So how does this works? How does this work? So the chain length is just evaluating. I can remove this. It's doing nothing but evaluating the a chain of three functions which are applied in sequence. That's it. We have a chain here. We provided it. Chain is a type that we customly created, right? And what we are doing, we are picking the three methods out of this chain, and we are just returning them in a sequence. And we have the input x is being passed to the first function, the output of the first function is being passed to the second function, and the output of the second function is being passed to the third function. That's it. The whole magic is there. So why would we do this? So if we have a composition of functions and we need to evaluate the final result, we do this. Now the chain derivative is computing the chain, the derivative of a chain of three functions using the chain rule of calculus. We do the same thing. We extract the functions, and then we have the forward pass. We compute the immediate result of f1 on the input range and f2 on what f1 produces. And then we have the backward pass. We've produced the derivative of f3 with respect of its input, which is f2. We do the same thing for the function f2 with respect to its input, which is f1. Same thing for the input range. And why would we do this? Because when you have a composition of functions, the derivative of the composition is not very straightforward. You need to apply the chain rule to compute the derivative efficiently. All right, so then we have these three functions. I'm going to remove the comments. Now this one plots all of this. This one's going to plot the chain. The other one is going to plot the derivative. Here we just provide the inputs to our derivative, and that's it. That's it. I think this should be the logic behind it. Now we can even compare the plots of the derivatives to the slopes of the original functions, and we can see that the chain rule is computing the derivatives properly. All right. All right, there's one thing that was unclear for me here, and it's why is the function falling here, but the derivative is for some reason rising. So it seems like that this is the way how each stage of it works. So okay, so the first part, and I'm gonna only focus on the part from -3 to 0, we have the leaky ReLU function, which introduces a small slope for x's that are less than 0. So the output is a negative value. Well, where is leaky? Leaky, it's here. So basically for x's that are going from -3 to 0, the output is a negative, is a small negative number. And I can, oops, I can maybe test it here. So leaky rel, maybe I can print. Maybe I can print. Is this gonna work? I hope it will. So leaky rel for the plot range, and maybe I can put here 0.5. All right. So I have negative values here. So this is the leaky ReLU. But now on the leaky ReLU, we have the square function that comes on it. So here we have the square function, and if I run it as well, we are squaring it. We are squaring these values. Now there are always the negative values from leaky ReLU become positive. So as x approaches 0, the squared output becomes smaller and approaches 0, right? So for example, what was the first value? Maybe I should have. So as we increase here, this value approaches 0, and now we have the sigmoid, which squashes these values into a range from 0 to 1. If I run this, all right, 5, 8, 9, 5, 6, 5, 3, 5, 2, 5, 0.9, 0.98, 0.99. So it seems like it makes sense, because at -3 we have 5.8. It goes maybe up until, where is it? -3, -2.5, 2, 1, 5, 1, 0, 5. This is the 0 version. It's exactly at 0.5, it seems, and then it slowly increases itself. So as x becomes more negative, leaky ReLU grows slowly, so the squared value decreases, and the sigmoid output becomes closer to 0.5, and this creates a falling curve. But why is the derivative rising from -3 to 1 to 0? So it shows the rate of change of f of x with respect to x. So from -3 to 0, the derivative graph rises even though the function itself is falling. Okay, this is because of the chain rule and how the derivative of each steps behave. So if I only Let me try. What was the first function? It was soliki rel u. Let me just do this and see what happens here. Length of input change should be 3. Fuck. Why have you bounded these methods to have chain 1? Maybe here. Leaky rel u, but it won't work again. I'm gonna get the same error, right? Yeah. I'm gonna get the same error. All right. So, okay, now let's talk about functions with multiple inputs. By this point, I have a somewhat of an understanding of how functions can be made into composites to form complex functions, and I learned on how to compute the derivatives of those functions. I learned how I can represent them as a series of boxes. But often the functions we deal with in deep learning don't have just one input. Instead, they have several inputs that at a certain steps are added together, multiplied, or otherwise combined. As we'll see, computing the derivatives of the outputs of these functions with respect to their inputs is still no problem. All right. Okay, so let's consider a new example here. Again, I'm pretty underwhelming when it comes to math, so hopefully I'll do this well. So these are the functions with multiple inputs. All right. So it says here, if our inputs are x and y, if our inputs are x and y, then we could think of the function as occurring in 2 steps. Okay, 2 steps. In step 1, if our inputs are x and y, then the function is occurring in 2 steps. All right. So x and y in step 1 are fed through a function that adds them together. We know that function is alpha, I think. We'll use Greek letter. Okay. So this is simply like this. A is the function that produces this. It's alpha x y, and it's x plus y. Okay. Now the step 2 would be to feed A through some function. Is this gamma or rho? It's sigma. All right, so the step 2 would be to feed A through some function sigma. Like this. Oops, sorry. So it's S equals sigma of A. All right, so now I haven't understood anything. Let's let's see how the diagram for this looks like. So we have functions with multiple inputs, and the diagrams with circles and arrows connecting them can be taught as computational graphs. All right, so what do I have here? I have the function alpha, right? And I'm having x being an input, I'm having y being an input, and then I have A, which is the product of this, which takes an input into, which is taken as an input into rho, well, actually sigma, it's not rho, sorry. And then I'm producing S. So we have a certain order of operations here. We have 2 inputs going into A and coming out as A and then being fed through sigma. All right, let's code this up. Hey Mario Bro 123. Sorry for not answering. I'm learning I'm following a book about deep learning, and I'm trying to understand how it works behind the scenes. I don't know, maybe change my profession or just because I want to learn something new. All right. So let's add a markdown first. How is this called? These are called functions with multiple inputs. Alrighty. Do I need to escape? Ah, okay, so it's escape, it's not enter. Then I'm adding code. Code here. So this is an example of a function with multiple inputs. I'm just gonna copy it, sorry. Nice. So what do we have here? We have a definition, multiple input set. We have two NumPy arrays. We have a sigma as well, which is an array function which produce the final value. So it's function with multiple inputs and addition forward pass. So I'm asserting that the shape is equal to, the shape of x is equal to shape of epsilon. I'm creating a, which is x plus epsilon. I'm returning the sigma of that. So this is alpha, and the sigma is another function that I'm taking here. All right. So what's the only thing that is a bit different? It's, I think, the assertion, because we are dealing with an operation that takes multiple ND arrays as inputs, and we have to check their shapes to ensure they have the same conditions for this operation. And for an operation such as addition, we need to check whether the shapes are identical, so that the addition can happen. All right, so the next step would be to calculate derivatives of functions with multiple inputs. I'm gonna do, because I realize I don't have a focus for like doing multiple hour streams. I think I'm gonna create multiple 1 hour stream throughout the day. So today, if I do deep learning again, I'm gonna continue with this. Otherwise, I'm gonna do a stream on another topic. So thank you so much.